Hello friends, this is Sujimna, belongs to CSCA section of Adishankara Institute of Technology. Today I am in front of you to explain my tech talk on the topic of breadth first search and depth first search, popularly known as BFS and DFS, in the topic Mathematical Foundation for Computer Science. Now, first of all, what is BFS? BFS stands for Breadth First Search. It is also known as Level Order Traversal. The queue data structure is used for the Breadth First Search traversal. When we use the BFS algorithm for the traversal in a graph, we can consider any node as root node. There is no particular node. Let us consider below graph for the breadth first search traversal. Suppose we consider node 0 as a root node, therefore the traversing would be started from node 0. Now the queue is filled with 0 as we have selected 0 as the root node. Once node 0 is removed from the queue, it gets printed and marked as a visited node. Once node 0 gets removed from the queue, then the adjacent nodes of node 0 would be inserted into a queue as shown below. We can see the adjacent node of 0 is 1 and 3, as we have inserted 1 here, and 0 will be popped out, deleted. So the result is 0. Now the node 1 will be removed from the queue. It gets printed and marked as a visited node. Once node 1 gets removed from the queue, then all the adjacent nodes of node 1 will be added in a queue. The adjacent nodes of the node 1 are 0, 3, 2, 6. Let me show. The adjacent nodes of 1 are 3, 0, 2, 6, 5. But we have to insert only unvisited nodes in a queue. As we have already visited 0, so we will be having remaining 3, 2, 6 and 5 are unvisited. Therefore, these nodes will be added in a queue as shown here. Here 3, 2, 5, 6. These are the adjacent nodes of 1 we have added in the queue. The result will be 0 and 1 as we have removed 0 and 1 from the queue. The next node is 3 in the queue. So node 3 will be removed from the queue. It gets printed and marked as visited as shown below. Here the 3 will be deleted and added in the result. Now once node 3 gets removed from the queue, then all the adjacent nodes of node 3 except the visited nodes will be added in a queue. The adjacent nodes of node 3 are 0, 1, 2 and 4. Since node 0, 1 are already visited, how we can know that these are already visited means here the result is containing 0, 1 and 3. So 0 and 1 are already visited and node 2 is present in a queue. Therefore, we need to insert only 4 in a queue. Here the adjacent nodes of 3 are 0, 1, 2 and 4. 0 is already visited. So 1 is already visited. So we have 2 and 4. 2 is already contained in the queue. So only 4 is remaining. So we have to add only 4. Only 4 and the 3 will be added in the result. Now the next node in the queue is 2. So 2 would be deleted from the queue. It gets printed and marked as visited below. So now the 2 is added into the result. Once node 2 gets removed from the queue, then all the adjacent nodes of 2 except the visited nodes will be added in the queue. The adjacent nodes of 2 are 1, 3, 5, 6 and 4. Since the nodes 1, 3 have already been visited, we have 5, 6 and 4. But we have 4, 5 and 6 are already added in the queue. Therefore, we don't need to insert any node in the queue. The next element is 5. So 5 would be deleted from the queue. It gets printed and marked as result. Now 5 is also added into the result. Now we are left with 6 and 4 in the queue. Once node 5 gets removed from the queue, then all the adjacent nodes of node 5 except the visited nodes will be added in the queue. The adjacent nodes of 5 are 1 and 2. Since both nodes have been already visited, therefore there is no vertex to be inserted in a queue. The next node is 6. So 6 would be deleted from the queue and it gets printed and marked as visited. So now the 6 also comes and added into the result. Now once the node 6 gets removed from the queue, then all the adjacent nodes of the node 6 except the visited nodes will be added in the queue. The adjacent nodes of 6 are 1 and 4. Since the 1 has been already visited and 4 is already present in the queue, there is no vertex to be inserted in the queue. The next element in the queue is 4. So 4 would be deleted from the queue. It gets printed. Once the node 4 gets removed from the queue, then all the adjacent nodes of node 4 except the visited nodes will be added in the queue. The adjacent nodes of node 4 are 3, 2 and 6. Since all the adjacent nodes have been already visited, so there is no vertex to be inserted in the queue. Now what is DFS? DFS stands for Depth First Search. In DFS traversal, the stack data structure is used. In previous one we are using queue data structure. Here we will be using stack data structure. In DFS, traversing can be started from any node, or we can say that any node can be considered as root node until the root node is not mentioned in the problem. If in the case of BFS, the element which is deleted from the queue, the adjacent nodes of the deleted node are added into the queue. In contrast, in DFS, the element which is removed from the stack, then only one adjacent node of a deleted node is added in the stack. To explain it more clearly, I came with an example. Let us consider the below graph for DFS traversal. Now first we insert the element 0 in the stack as shown below. We have considered 0 as the root node, so we have pushed 0 into the stack. Now the node 0 has two adjacent nodes. Here node 0 has two adjacent nodes, that is 3 and 1. Now we can take only one adjacent node, either 1 or 3 for traversing. Suppose we consider node 1, therefore 1 is inserted in a stack and gets printed as shown below. Now we can see 0 and 1 in the stack. Now we will look at the adjacent vertices of node 1. The unvisited adjacent vertices of node 1 are 3, 2, 6, 5, 3, 2, 5 and 6. We can consider any of these 4 vertices. Suppose we take node 3 and insert into the stack as shown below. Consider the unvisited adjacent vertices of node 3. The unvisited adjacent vertices of node 3 are 2 and 4. We can take either of the vertices, that is 2 or 4. Suppose we take vertex 2 and insert it in the stack as shown here. The unvisited adjacent vertices of node 2 are 5 and 4. We can choose either of the vertices, that is 5 or 4. Suppose we take vertex 4 and insert it in the stack as follows. Now we will consider the unvisited adjacent vertices of 4. The unvisited adjacent vertices of node 4 is node 6. Therefore, the element 6 is inserted into the stack as shown below. After inserting 6 is the last vertex. We will look at the unvisited adjacent vertices of node 6. As there is no unvisited adjacent vertices of node, so we can't move further. This is the last one, so we can't move further. So we need to go for backtracking. The topmost element in the stack is 6. Would be popped out from the stack. Here the 6 is popped out and added into the result we have 6 now. The topmost element in the stack is 4. Since there are no unvisited adjacent vertices left of node 4, the adjacent vertices of node 4 are 3, 2, 6. So we have 3, 2 already present in the stack and 6 is already got into the result. So there is no unvisited vertices. So the 4 is also popped outside and added into the result. Now we have result as 6 and 4. The next topmost element in the stack is 2. Now we will look at the unvisited adjacent vertices of node 2. Since only one unvisited node, that is 5. So 5 is left unvisited, so node 5 would be pushed into the stack above 2 and gets printed as shown below. Now this is the stack we are having. Now we will check the adjacent vertices of node 5 which are still unvisited since there is no vertex left to be visited. So we pop the element 5 and we will be adding this 5 into the result. Now we have 6, 4 and 5 in the result. Now we cannot move further 5, so we need to perform backtracking. As 5 adjacent nodes all are visited, we need to go for backtracking. In backtracking, the topmost element would be popped out from the stack. The topmost element is 5. That would be popped out from the stack and we move back to 2, and here we can clearly see that from 5 it is going back to 2. As there is no adjacent vertex left to be visited, so we perform backtracking. In most backtracking, the topmost element 2 would be popped out. The 2 would be popped out and will be added into the result. We have 6, 4, 5 and 2 as the result. So, now we will check the unvisited adjacent vertices of 3. After removing 2, we have 3 as the topmost element of the stack. After checking the unvisited nodes, we have no unvisited nodes. So the 3 is also popped out. Now we have 6, 4, 5, 2 and 3 as the result. After 3 it is going to 1. So it will check whether 1 is having any unvisited nodes or not. We have find nothing unvisited nodes, so the 1 is also removed from the stack and is added in the result. So we have 6, 4, 5, 2, 3, 1 as the result. Now the 0 node is checked for the unvisited nodes. No unvisited node is found. So the 0 is also taken out and added into the result. Now we have 6, 4, 5, 2, 3, 1, 0 as the result. As we observe in the above figure that the stack is empty, so we have to stop the DFS traversal here, and the element which are printed is the result of the DSL traversal. So thank you guys, hope you have understood. Thank you once again.